Dear friends, in this video we study the behavior of a special mechanism called double pendulum. As represented in the drawing, this mechanism is made of two bars. One swings on a fixed pivot and the other swings on the first one. The system has 2 degrees of freedom represented by the angles and is only affected by the gravity force, apart from the reactions. Here we will study the dynamic problem by means of the Lagrangian method already introduced in a previous presentation. As usual, we will check the experimental results with the theory to learn a lot of interesting things. I'm sure it's going to surprise many of you. Let's see together. In the beginning, we introduce the problem. Then we start the experimental phase. First, the case with 90 degrees starting angle, then with 60 degrees. These starting angles are same for both bars. After the experiment, we will study the problem analytically by using the Lagrange method. The result is also visualized by means of the animation using the program GEOGEBRA. Finally, we discuss the results found by the theory and the ones in the experiments. We remember that this video is made of two parts. First part is dedicated to the great swings and the second to the small swings. That is the reason why we refer here to the experiment 1 and model 1. Those results will be recalled in the second part of the video. This is a double pendulum made of one bar which is free to swing on a fixed pivot and the second bar which can swing around a movable pivot. Okay? And the task of today is to find the motion equation of such a mechanism and understand if this motion is predictable or not. Let's start together. The mechanism of the experiment is schematized hereby. It consists of two rigid bodies, two equal bars with following constraints. The bar number 1 has a pivot at one end that is fixed, capital O, and another pivot at the other end, capital K, in common with the bar number 2. The bar number 2 is joined with the bar number 1 at the same pivot, capital K, being capital K not at one end. The coordinate system is so defined. The x-axis is horizontal and starts at the same pivot, capital O. The y-axis is vertical towards the bottom. The angle theta is the angle between the bar 1 and the axis y, positive if counterclockwise. The angle phi is the angle between bar 2 and axis y, also positive if counterclockwise. The system has 2 degrees of freedom, and this makes the solution of the dynamic problem something more complicated. Before starting the experiment, we collect the relevant measurements, also lengths and the weights. The length of the bar is 27 cm. That is the distance between pivots capital O and capital K. This distance is fixed. In this video, the length unit is meter. The distance of the pivot capital K from the center of gravity of the bar 2, that is G2, we call D, and it is 2.5 cm. We have already defined the angle theta and phi in the previous slide. The weight of the bar is 0.2 kg. For the first experiment, we consider as starting condition both theta and phi equal to 90 degrees. The experiment we repeat twice and we represent the outcome in the slide as movie with slow motion. It shows a periodical swing of the theta angle that is approximately 1.1 second. Moreover, we observe that the trials are repetitive for a short while, let's say for about 3 cycles, and soon after they are not. The motion of the two bars diverge. We took a couple of shots for t equals 4 seconds and we observe how different are the two configurations. One shows negative 18 degrees and negative 50 degrees for the angles theta and phi respectively, and the second 11 degrees and 75 degrees. We can argue that the positions, at least after a certain time, are not predictable and the motion is chaotic. The second experiment has equal geometrical parameters apart from the initial conditions. Here the angles theta and phi are both 60 degrees. We repeat the observation with the same method, taking two videos using a slow motion camera. In this case we observe a period of about 1 second for the angle theta, and also in this case the motion is repetitive for the first 3 periods more or less. Another couple of slow motion frames are used to identify the different configurations after 5 seconds. In the first trial we see 40 degrees for both theta and phi. In the second, 20 and negative 60 degrees respectively. Also in this case we can declare the motion is not repeatable and shows a chaotic behavior. As seen in one previous video, we want to solve the problem analytically by using the Lagrangian theory. The only assumption used in the model is that there is no friction. The method says we need to write the potential energy of the system, capital V. That is only gravity potential energy. The potential energy of the system is the sum of the potential energy of each bar. The formal expression is always the same, also negative capital M G Y, once for bar 1 and once for bar 2. We remember that y1 and y2 are the vertical coordinates of the center of mass of the bars. Now we need to express y for the first bar as function of the angles theta and phi. Actually, y1 only depends upon theta and its expression is L half into cosine theta. Y2 does depend upon both variables instead. Its expression is here represented. The potential energy of the system is also written here in red. We take the first partial derivative of capital V with respect to theta and the first partial derivative of the same function with respect to phi, and we put those equal to 0. The equilibrium positions are 4, theta equals 0 pi, phi equals 0 pi. We have represented those 4 positions here aside with respect to horizontal axis x. Let's assess now which positions are stable and which not. For doing that, we write the second derivative of capital V with respect to theta. That turns into 3/2 of mg into L cosine theta. And we calculate its value for the first equilibrium point 0, 0. This value is positive. Then we write the second derivative with respect to phi, and we calculate it also in the same point. Finally, we write the mixed derivative, that is 0. With the above three derivatives, we build the Hessian matrix and we calculate its determinant, that is positive. Since both the Hessian determinant and the first element of its matrix are positive, the position 1 is stable. If we repeat the procedure for the three remaining equilibrium points, we assess that they are unstable because either the Hessian determinant or the first double derivative is negative. Once the static problem is solved, we can treat the dynamic one. The kinetic energy T is the sum of kinetic energy of the single bodies, also T1 and T2. The first body is just rotating around the pivot O. Therefore, its kinetic energy is only rotational. Its expression we can find here, where capital I0 is the moment of inertia of the bar with respect to the pivot capital O. The kinetic energy of the second body has two contributions instead, the translational and the rotational one. The translational has the expression 1/2 of m into Vg2 square, where Vg is the speed of the center of mass, capital G2, of the second bar. The rotational has the expression 1/2 capital Ig2 into phi dot square, where capital Ig2 is the moment of inertia with respect of its center of mass. Below are the expressions of the two moments of inertia for our application. How to determine Vg? By definition, the speed is the derivative of the position, and the position is a vector. The vector OG2 we can write as sum of OK and KG2. Replacing the values as function of theta and phi and using the versors I and j of the coordinate axes x and y respectively, we find the expression at the right side. Its derivative gives the velocity of the center of mass as vector. Finally, we get the translation kinetic energy of the bar 2 by multiplying 1/2 of the mass by the velocity vector square. After phi adjustments, the kinetic energy of the system assumes the expression displayed in red. Since we have now both capital V and capital T, we can write the Lagrangian function capital L of the system. We remember that capital L is a function of two variables, theta and phi, and also its derivatives. The first motion equation is given by the Lagrange formula with partial derivatives with respect to theta. The second motion equation is written in a similar way with partial derivatives with respect to phi. We get the equations in red. If we call capital A 4/3 of L, capital B d into cosine theta minus phi, and C L over 12 plus d square over L, then we can simplify the equations above in a way to put the second time derivatives of theta and phi on the left side. We recognize that the function at the right side of the equation 1 is only function of theta, phi and phi dot, while the function at the right side of equation 2 is only function of theta, phi and theta dot. If we introduce the matrix capital M displayed in blue, then we can write the two equations in a matrix form. Eventually, we can solve for theta double dot and phi double dot by inverting the matrix capital M as displayed. The expression of the solution we can write here, where the determinant of the matrix capital M is capital A into capital C minus capital B square. Now we have two solutions, individually for theta double dot and phi double dot. We call the solutions G1 and G2 respectively. Those are both functions of theta, phi, theta dot and phi dot. At this stage, we need to solve the differential equations with a numerical algorithm. To make it simple, we introduce the Euler method, that is less sophisticated than the better known Runge-Kutta one. The starting condition says for t equals 0, theta equals theta 0, phi equals phi 0, theta dot equals 0, phi dot equals 0. From those data, we calculate the functions g1 and g2 that give theta double dot and phi double dot respectively at the same time frame. This is the step 0. The step 1 takes t equals delta time, then theta dot equals theta 0 plus theta double dot into delta time, and similar expression for phi dot. Theta is then given as theta 0 plus theta dot into delta time, and similarly for phi. Eventually, the new theta double dot and phi double dot are calculated with the functions g1 and g2 using the found calculated step values for theta, phi, theta dot and phi dot. When all the steps are calculated, we summarize the result in a table whose first rows are displayed here. The starting conditions, the constants, and the other parameters are listed aside. The time frame here is 0,10 seconds and delta time 0.002 seconds. In the right upper chart, the calculation results for the angles theta and phi. We notice that theta is almost periodical with a period of 1.1 seconds, even though its amplitude changes from 90 to 70 degrees. Phi is not periodical instead. If you repeat the calculation for another starting condition slightly different, for example 89 degrees for both angles, the result dramatically changes. Overlapping the two charts, we notice that the solutions are matching only till 3 seconds, more or less, and then they diverge. When the solution is highly sensible with the change of the initial conditions, we say mathematically that the system is chaotic. The behavior is confirmed by the experimental trials. Let's see now what happens if you reduce the starting angle to 60 degrees. We observe that the function theta is still something periodical. This time the period is 1 second. If we change the angle to 59 degrees, we observe a substantial change of the angle phi. Also in this case, by overlapping the two charts, we recognize that the motions become chaotic after a time that is approximately 3.5 seconds. We run here an animation of the double pendulum when starting condition 90 degrees and we compare with experimental data. The animation has been achieved by using the program GEOGEBRA. The theoretical and experimental values are substantially matching for the first 1.5 period and then diverge. In this case also takes an effect, the friction, that unfortunately we have neglected in the model. In this slide, we compare two positions of the pendulum at the time 3 seconds, once when the starting angle is 90 degrees and once with 89 degrees. We observe that the angles are substantially different each other. Some observations. The system dynamics does have an analytical solution. The solution theta of time is almost periodical. The solution phi of time is not periodical at all. Within a short time, let's say more or less 3 periods, the experimental result is repetitive, the motion is predictable, and experimental and theoretical results are matching each other. For the long time, let's say more than 3 periods, the experimental result is not repetitive, the motion cannot be predicted, the experimental and theoretical results are not consistent each other. As a conclusion, we can say that the greater is the starting angle, the less is predictable, and the motion evolution is chaotic. The presentation of today has shown the behavior of a mechanical system, a double pendulum, for special starting conditions, that is, with big angles. We see that the motion is predictable and repetitive only for a short while, and soon after it turns chaotic. This behavior we encounter in many other fields of the science, like meteorology. We know how we are able to foresee the weather over a few days, but not farther beyond. In the next presentation, we see if, for the same mechanism, do exist conditions where the motion is predictable for a long term. Thank you for your attendance and see you next time. Bye bye.